Welcome to Naradar Academy. In this video, we are going to discuss about linear transformation, some of its properties and kernel of a linear transformation. See, linear transformation is nothing but a homomorphism from a vector space to another vector space. That is, let us take two vector space V and W over the same field F. Okay, if there is a mapping T from V to W which satisfies the condition T of U plus V equal to T of U plus T of V and T of alpha U equal to alpha into T of U, then that mapping is called homomorphism or linear transformation. Okay, right. Instead of having these two conditions, we can check whether T of alpha U plus beta V is equal to alpha into T of U plus beta into T of V, where this U and V are vectors from the vector space V and alpha beta are scalars from the field F. Okay, so if this condition is satisfied, then what we say? The given mapping is a linear transformation. If our linear transformation is also a 1-1 mapping, then it is called monomorphism. What do you mean by 1-1? That is, if you take two distinct elements in the domain, their images will also be distinct in the codomain. That means if you take u1 and u2 here in V, okay, u1 and u2 if you take here, T of u1 and T of u2 will also be different. Okay, for distinct elements have distinct images. That kind of mapping is called 1-1. If the linear transformation is 1-1, it is called monomorphism. Suppose if the linear transformation is onto, then it is called what? Epimorphism. Onto means every element in the codomain. Okay, this is domain and this is codomain. No, every element in the codomain, if it has a pre-image in the domain, it is called onto mapping. So, if the linear transformation is onto, it is called what? Epimorphism. Suppose if the linear transformation is both 1-1 and onto, then it is called as isomorphism. Okay, right. Next one is functional. Functional means, suppose you see here we have taken V as the vector space and F as the field. No, suppose if we define a linear transformation from V to F, then that linear transformation is called a linear functional. So what do you mean by linear functional? It is a linear transformation from the vector space to its field. Okay, this is called what? Linear functional. Now let's see some example for linear transformation. Suppose T from V to W is defined as T of V equal to 0. That is, for every vector V in capital V, the image is what? 0. Okay, we have to check whether this kind of transformation is a linear transformation or not. So, let us take UV in the domain and alpha beta from the field. Now consider T of alpha U plus beta V. By definition, what is T? T for any element of V is equal to what? 0. So, T of alpha U plus beta V is also equal to 0. Now consider the right hand side. What is the right hand side? Alpha into T of U plus beta into T of V, no? That is also equal to alpha into 0 because T of V equal to 0 for every vector plus beta into 0. So both left and right hand sides are 0. That means T of alpha U plus beta V equal to alpha into T of U plus beta into T of V. Therefore, this is a linear transformation. Next one is, and this transformation is called trivial linear transformation. That is, mapping every vector to 0 is called a trivial linear transformation. Next example is, T is a mapping defined from V to V as T of V equal to V. Okay, that is every element is mapped to itself. This is called identity mapping. We are going to check whether this is a linear transformation or not. So, let us consider T of alpha U plus beta V, where this U and V are elements of V and alpha and beta are elements of the field F. Okay, so this is equal to, so what is the definition here? For every element, the image under T is equal to the element itself. So, it's equal to alpha U plus beta V. Okay, right. So, it's equal to alpha into, instead of U, what can I substitute? T of U. And similarly, instead of V, I can substitute T of V. So, alpha into T of U plus beta into T of V. So, what we get finally? T of alpha U plus beta V equal to alpha T of U plus beta T of V. Therefore, this is also a linear transformation called identity linear transformation. Then the next one, let T be a transformation or T be a mapping from V to V by W. This is what? Quotient space. Already I have posted on video regarding vector spaces and vector subspaces. I have given the link in the description box. If you want, you go through that video. This V by W is called quotient space. So we are defining a mapping from V to V by W as T of V equal to W plus V. That is, every element V of the vector space is mapped to W plus V in the quotient space. We are going to check whether this is a linear transformation or not. Okay, so for that what I am taking is, consider T of alpha U plus beta V equal to, what is the definition? W plus that vector. So W plus alpha U plus beta V. Okay, let us take this as equation number 1. Now let us consider the right hand side. Alpha into T of U plus beta into T of V equal to alpha into, what is T of U? W plus U, and T of V is W plus V. Okay, right. Now this can be written as, see, this alpha is an element which is taken from the field. Okay, so when you multiply this alpha with W, that you will get it as W only. Okay, so W plus alpha U plus, similarly here also beta into W is W only. Okay, W plus beta V, right? Okay, then why I am saying alpha into W is equal to W means, W is also a vector space, no? In vector space, if you take one scalar and vector and if you multiply, that will again become a vector of W. Okay, right? So when you take this alpha into W, that will give you only the elements of W. So alpha into W is simply alpha, and similarly beta into W is also simply what? W. So what we have? W plus alpha U plus W plus beta V. But this is nothing but what? What can you write? W plus W is equal to W only, because if you add elements of W with itself, you will get again the space W plus alpha U plus beta V. So what you get? W plus alpha U plus beta V. But by this definition, this is nothing but T of alpha U plus beta V. So what we have proved? That is, T of alpha U plus beta V is equal to alpha into T of U plus beta into T of V. Therefore, this T also represents a linear transformation of V to V by W. Okay. Then next one, let T be a mapping from V to W. Let it be a linear transformation. Then what we have to prove? T of V is a subspace of W. Okay, this is a result that we are going to prove. That is a linear transformation. T from V to W is a linear transformation. I have to prove the image, that is T of V, image space is a subspace of W. So what is the definition of subspace? If you take any two elements, their linear combination should also be there. Take two elements of T of V, find out the linear combination. If that linear combination also belong to this set, then it is called a subspace. Okay, now let us take two elements V1, V2 in capital V. Okay, and alpha, beta belongs to F. Now, what is this T of V1? Let it as W, and T of V2, let us take it as W2. Okay, these two are images, no? So they belong to T of V. Okay, they belong to T of V. Now, consider alpha W1 plus beta W2. We have to prove this also belong to T of V. For being a subspace, this linear combination, that is, when you take two elements W1, W2 belong to T of V, we have to prove their linear combination alpha W1 plus beta W2 also belong to T of V. Alpha W1 plus beta W2 is nothing but alpha into T of V1 plus beta into T of V2. It's equal to, now since T is a linear transformation, no, this can be rewritten as T of alpha V1 plus T of beta V2. Okay, then again, since T is a linear transformation, we can combine these two terms. So T of alpha V1 plus beta V2. But this belongs to T of V, no, because T of any vector belongs to T of V. So what we have proved? By taking two elements in T of V, we have proved their linear combination is also in T of V. That implies T of V is a subspace of W. Okay. Sorry, it's a subspace of W, not V. It's a subspace of W. Next one, if V and W are vector spaces over the field F, then let us take one linear transformation from V to W. Kernel of the linear transformation is defined as set of all v belong to v for which t of v equal to 0. See, this kernel is nothing but, see here, these two are vector spaces, no? Here you will be having the identity element is there, no? Since this is a vector space, this will be an abelian group with respect to addition. So definitely it will have an additive identity. That additive identity is taken as 0 here. So we have to look at the elements of V which are mapped to the additive identity of W. Okay, the set of all collection of elements of V which are mapped to the additive identity. It is called kernel of T. Okay, this kernel of T plays many important role in vector spaces. Okay, let us see some of them here. Let T from V to W be a linear transformation. Then T is a monomorphism. Monomorphism means what? Linear transformation with one condition. If and only if kernel of T equal to singleton 0. That means only the additive identity of V is mapped to additive identity of W. Then we can say this T is 1 mapping. Okay, that is only one element. That is the additive identity of V is mapped to additive identity of W. No other element is mapped to 0. In that case, T become what? Monomorphism. Okay, next one is fundamental theorem of homomorphism. This theorem states, let V and W be vector space over field F. T from V to W be an epimorphism. What do you mean by epimorphism? Linear transformation along with onto condition. Then the kernel of T is a subspace of V, and V by V1 is isomorphic to W. Okay, I am not going to give the proof here. These are the things which we use for doing problems. So I have given the statement alone. So what is the one? Kernel of T we have defined previously. No, this kernel of T is a subspace of V. That is one result. Another result is the quotient space V by V1 is there. No, that is isomorphic to W. Okay, then another result. V is a vector space over a field F, and A and B are subspaces of V. A and B are subspaces of V. In that case, what we have? A plus B by A is isomorphic to B by A intersection B. These are important results that I am stating here without giving the proof. So, remember the statements. Then, next one. Let V and W be vector spaces over a field F, and let L of V comma W be the set of all linear transformations from V to W. Then L of V comma W is itself a vector space over F. So already we have two vector spaces over F. I am collecting all the linear transformation. Different linear transformation we can define from one vector space to another vector space, no? For example, trivial linear transformation, that is mapping every element of V to 0 of W. That is one linear transformation. Another one is identity linear transformation. In that way, we can define so many linear transformations from one vector space to another vector space. Collect them all together. That will also form a vector space over F. This is the next statement. Now let us do some problems. So now in the following problems, I have taken the problems which I have already discussed in the previous section. Okay, so what I am finding here in this set of problems is what is the kernel and whether it is 1 or on 2. So in the following set of problems, these are the things we are going to identify. Okay, T from V to W defined by T of V equal to 0 for all V belongs to V. That is, what is this? Trivial linear transformation. Already in the previous section I have proved this is a linear transformation, so I am not going to prove it here. Simply I am going to find what is the kernel and whether it is 1 or on 2. That is only I am going to find out here. See, every element of V is mapped to what? 0. That means kernel of T is the entire V, because all the elements of this V is mapped to 0, no? So kernel of T equal to V. And so since it is equal to V, it is not 1, because we have seen one theorem, no? If it is 1, kernel of T should be singleton 0. So it is equal to entire V, therefore it is not 1. Also it is not onto, because in the codomain, this is the codomain, no? Here only this 0 element is having pre-image. Remaining elements will be there, no? In W. You may be having several elements in W. So they are not having pre-images. Therefore, this is neither 1 nor on 2. Okay. Then next one. T from V to V defined by T of V equal to V. That is the, what is this? Identity mapping. identity mapping already I have proved that is a linear transformation. Now I am going to find what is the kernel and what is the property of that kernel. Now only, that is, the every element is mapped to itself means there will be only one identity, additive identity here. Therefore that 0 is mapped to 0. Therefore for single element, okay, therefore kernel of t equal to what? Singleton set 0. Therefore by that result, if kernel of t is equal to 0, it is a 1-1 mapping, but it is not onto. Why it is not onto? Because I think this has to be onto, because this is an identity mapping, no? Sorry, this is onto, right? So it is both 1-1 and onto. Next one is v from t from v to v by w defined by t of v equal to w plus v. Now this is what? Quotient space. We are defining this mapping t of v equal to 0 when w plus v equal to 0, right? That is 0 plus w. So what is kernel? Kernel is the entire w. Okay, because here if you say 0, what do you mean by 0? I already told you, no, that is the additive identity of the codomain. Here the codomain, all the elements will be like w plus v1, w plus v2, w plus v3, etc. So the additive identity of this is by definition we are writing, but for this particular problem the additive identity of v by w is 0 plus w. Okay, so w plus v equal to 0 plus w means what? The kernel, that is the kernel is equal to the entire w. Okay, right. Therefore since the kernel is not equal to singleton 0, what we have? It is not 1-1, but it is onto, because every element here has a pre-image here, because here the elements will be like what? v1 plus w, v2 plus w, etc. So every element here will have a pre-image. Next one is T is a mapping from v3 of r to v3 of r defined by T of ABC equal to a0, 0. That means for every point in the three-dimensional space R3, we are mapping it to points on the real axis. That is, sorry, not on the real axis, points on the x-axis. A0, 0 means what? X-axis. So when will you have the image equal to 0? That is irrespective of B and C. T of ABC equal to what? A0, 0. So it is mapped to 0, 0 means what? A is equal to 0. So B and C can be anything. That means whatever values B and C take, T of ABC is mapped to 0, 0, 0 for A equal to 0. Therefore, the kernel is 0, BC, where B and C are real numbers. Therefore, this is not equal to singleton 0. Therefore, it is not 1, 1. Also, this is not onto, because you see the elements are mapped to what? 0, 0 only, no? That is A 0, 0 only. So, when these elements have non-zero values, they don't have any pre-images. Therefore this is not onto. This is neither 1, 1 nor onto. Okay, that's all. I hope you understand this video. That's all. Thank you.